Right now, there's a massive race to build the next supercomputers. But to work, we must chill the hardware until it's colder than deep space. The tech industry's best solution so far is a big freeze. We build these incredibly complex towers of gold plates and silver wires, essentially creating the world's most expensive refrigerator just to hold a few bits of data. The problem is the chips inside. Look at this close-up of a modern processor. It's a physical maze. Even our best hardware is still stuck on a single track, fetching one instruction at a time and executing it before it can move to the next. Think of the processor as an exhausted librarian. Every time it needs information, it physically runs down a hallway, grabs a book, and runs back. Try doing 1,000 things at once, and the hallway crowds. The friction generates heat, and the system stutters. We've reached a limit because we're treating computers like little delivery drivers, forced to run errands. This physical back and forth is what's keeping our technology from reaching its true potential. But what if the answer isn't a colder freezer? What if we could stop the librarian from running altogether by changing the math behind the machine? Instead of a calculator that grinds through lines of code, imagine a computer that works like a precise measuring tool, observing a mathematical universe that's already there. If we stop forcing data to move back and forth across a chip, we stop the friction. And without that friction, we can finally stop worrying about the hardware overheating. To understand how this works, think of a radio. The room you're in right now is actually full of music and voices, but you can't hear them because they're all on different frequencies. They're invisible waves, just waiting for you to listen. In this new system, we don't send data through a hallway. We give the computer a set of coordinates, and it tunes into the data's specific frequency. It doesn't move to the data, it's just there. This eliminates the hallway entirely. Because the answer is found through a unique vibration, there is no physical trip for the processor to take. This is why multiple different systems can all live in the same space at once. Each one is on its own isolated channel, so they can exist together without ever bumping into each other. By finding data through resonance rather than movement, we get rid of the lag and the jitter that makes traditional computers slow down when they get busy. Usually, when a computer tries to do 10 things at once, it's actually frantically juggling them, dropping one to pick up the next. This constant switching is what creates software lag. This system replaces the juggling with a single conductor. Think of it like a hand crank that's connected to every single wave in that cosmic radio at the same time. When that crank turns once, every single system and every application moves forward together. Everything stays in perfect sync. This hive mind way of working removes the chaos of multitasking, allowing thousands of processes to run in total harmony without a single stutter. This approach actually mimics the way nature works at the smallest levels. In physics, things can exist as clouds of many possibilities, only snapping into a solid, definite shape when they are measured. This architecture works inside a massive mathematical noise field, an ocean of data that fills every part of the system. Much like a radio station is always there in the static, your data isn't stored in a physical box. It's pulled out of that noise the moment you tune in to its unique vibration. This system doesn't just pretend to be fast. It uses the same hidden patterns of math that the universe itself uses to keep things organized. The future of high-speed computing doesn't have to look like this. Massive football fields of servers that require a power plant to stay cool. By treating data as a mathematical coordinate, we can take a standard, older computer and give it the ability to solve problems with the same precision as the world's most powerful machines. We aren't building bigger calculators anymore. We are finally learning how to tune